Hi, this is a hypothesis test question. I'll be doing part one on it, which is to test the variance. So the question goes, a new process to assemble a device is introduced in the hope of reducing the overall assembly time for the device. Data for holding the old process and the new process are shown below in the table. Assembly times are in minutes. So here's the table. There's the old process and all the times there in minutes, and this is the new process and all the times in the second row in minutes. Assuming the data comes from two normally distributed populations, test at the 5% level of significance that 1. The data for the old process is more variable, and 2. The mean assembly time for the old process is greater than the mean assembly time for the new process. So we'll do part one now. We're going to find out if the data for the old process is more variable, and it's worth 10 marks. So the whole point of this is that it is a hypothesis test. So we have to make a hypothesis first of all, and there's a lot of marks going for stating the hypothesis. So we have a null hypothesis, H0. And the null hypothesis always states that there is no difference, i.e. that the things are the same. So in this case, what we're looking at is the data for the old process is more variable. Now, variable is the word that is related to variance. So we're talking about variance here. So variance is denoted by sigma squared. So we're saying that sigma squared 1, where 1 will denote the old process, is equal to sigma squared 2. So basically the null hypothesis is stating that the variance for the old process is exactly the same as the variance for the new process, that there are no differences. Our alternative hypothesis just call that H1. Our alternative hypothesis is what we're going to test in the question, and it says that the old process is more variable. So here we're going to have the old process, which is sigma 1. The variance of the old process, sigma 1 squared, is greater than the variance of the new process, sigma 2 squared. So you need to state that in the question, okay? So then the next thing is that to do this, we have to sort out the data. But if you want, you can decide on which formula you're going to use for it, okay? So at the back of the exam book, you'll be given a list of formula. Here it is here. It's a bit small, so I'm raising it up. Now there's only these, this is under the tests, okay? The hypothesis test, Z test and T test, they test the difference in the means. Then we have the F test, and you can see the formula for the F tests includes an S squared and sigma 1 squared and sigma 2 squared and S2 squared. So because it's got the sigma 1 squared and the sigma 2 squared, this must be your formula, if you don't already know, okay? So that's what we'll write down. Now there's a long version of it, but everything cancels out, so we're really left with a small version, which is F, the F test is equal to S1 hat squared over sigma 1 squared divided by S2 hat squared over sigma 2 squared. Now, the S hats are from, these are statistics from sample, okay? And this stuff up here, all these numbers up here, these are sample statistics, okay? But the sigma 1 squared and the sigma 2 squared, they're from a population. Now we don't know their answers. We're trying to make some inference about things to do with the population. But they're to do with the population, right? Because they're sigmas. But also because of our null hypothesis, we're hypothesizing that they are exactly the same. So if we're hypothesizing that the variance of the old process is the same as the variance of the new process, they can cancel out. So all we're left with then for our formula is S1 hat squared divided by S2 hat squared. Okay, so what we use now is we're going to use a calculator and use data up here. So the data is, we will do the old process first, so we can call that variable 1, right? And we're going to input this into statistics so that we can get the mean, the standard deviation, and the non-biased standard deviation as well. So let's have a look at that. So to do that, we go into mode setup, right? Can you see that? We go into mode setup, then we press 2 for stat, and then we press 1 because that will give us 1 bar. and I have a X column and a frequency column. The frequency column is not necessary for this, but it's good to have it on your calculator for other questions. So I input the data now, 32, 37, 35, so I just do 32 equals 37 equals 35 equals. Then 28, 41, 28 equals 41 equals 44 equals 35 equals 31 equals 34 equals 38 equals, and 42 equals. So now I have input the data. There are 11 pieces of data here, and there are actually 11 numbers there, so that coincides. And then to find out what the data, what the mean is and stuff like that, we do AC shift 1. And then we're looking at variables, so I press 4. And it gives me up n, that's the number, which we know is 11. 2 is x bar, so I'm going to press 2 and get the value of the mean, 36.09. So here, down here, I write the old process. And I can call that n1 equals 11. x1, the mean, x1 bar for the sample is 36.09. And then do AC shift 1 again, and 4 to get me into variable, and I'll go for 3, which is either S or S hat. I will find that out. The calculator doesn't know if I'm putting in a sample or the total population, so it's going with sigma and S here, and we will have to decide. So in this case, S for sample 1, the standard deviation for sample 1, that's 3. That equals 4.679. So just say 4.68. AC shift 1 and 4 again, and press 4. Now we get another standard deviation, which is 4.91. Now, this one is S hat, the larger one is S hat. It is an unbiased estimate of the standard deviation. Okay, so then we do the same again for the new process. So I'll get rid of that, and then mode setup, 2 for stats, 1 for one variable, and I put in these details here now, so it'll be 36 equals 31 equals 32 equals 31 equals 34 equals 36 equals 29 equals 41 equals, and 31 equals. Then now there's only 9 pieces of data here, and there is only 9. You see there's 2 less than there. Then you do AC shift 1 and 4 again on this calculator. So 1, we know that's 9, so I can put down, and this is the new process, we'll call this 2, okay, this one's called 1, so n2 is equal to 9. Then I will get the mean, which is 2 in my calculator, so x bar, the mean, x bar 2 is equal to 33.44. AC shift 1 and 4 again for variable. 3 is going to give me the value 3.499, 3.50, and then shift 1, 4, go for number 4, another standard deviation, and I'll get S, this is S2 equals 3.71. So again, this is S hat, a slightly larger one. Right, so all we do now is we can put in these values into this formula, so it's S1 squared, or S1 hat squared, so that's going to be 4.91 squared over 3.71 squared, and see what that gives us. So now to get out of this here, the stat mode, press mode setup, and I'm going to go back and do 1 for compute. So now I put in my fraction, and it's 4.91 squared over 3.71 squared equals 1.75. That's enough. Well, I just write down another 2 if I need it. Okay. Okay. So now this here is, this is the F, this is calculated from our data. Right? And the data is normally distributed, therefore we can use the F tables to calculate the F critical from the tables. So F critical from the tables. Now there's a few things we need to take note of here, right? The level of significance is 5%. That means now that you will be given tables during the exam. On the back of the tables there will be 3 sheets of F tables, and they will be at different levels of significance, the 10%, the 5% and the 1%. Now in this case we're looking for 5% level of significance. So in the F tables it could be written as 5% or it could be written as 0.05. Either one of them, okay? And this is a one-tailed test because we are only looking at one side. We're only looking at sigma 1 squared, i.e. the variance for the old process is greater than the new process. That's only one-tailed. If it had been that it was not that the variance of the old process was not equal to the variance of the new process, there were 2 possible options there, i.e. that the old process has more variable or that the old process is less variable. So that would be 2 tails. But in this case we're only looking at one side of the tail, so this is a one-tailed test. Okay, so you go to your F tables. Now I don't have them with me because the college is locked. I'll just use this here variation of them, okay? So it's the F tables. It's at the 5% level of significance. It could be written like this. And the other thing is the degrees of freedom. Okay, the degrees of freedom are given as n minus 1 and n minus 1 if you want. So for the first one it's going to be 11 minus 1, which is 10, and 9 minus 1, which is 8. So our degrees of freedom are 10 and 8, and that's like the x and the y if you want. We go along the horizontal. So I've drawn up a attempt at the tables, right? The F tables V1 and V2 here. So our first degree of freedom is 10 for the old process. So we go along to 10 here. And the second degree of freedom here was 9 minus 1, which was 8. So we go down to 8 there. So we read down 10 and then to 8, and we get 3.35. So that is what the critical value on the F tables will give us. So on the F tables, it is 3.35. Now what that means is, here's the F tables, right? F 10, 8. The F distribution looks like this. Here's the 5% here and there. This area here is do not reject the null hypothesis, H0, okay? Right, and the critical value we have from the tables is 3.35. So if our number from our data was greater than 3.35, it would be in here and we would reject the null hypothesis. But the number from our data is 1.752. 1.752. It is less than 3.5. It is in this area here of do not reject the null hypothesis. So we do not reject the null hypothesis. So as a final answer, you would say as 1.752 is less than 3.35, do not reject the null hypothesis. We cannot conclude. We cannot conclude that the variance of the old process is greater, or that, go with the words in question, that the old process is more variable. We cannot conclude that the old process is more variable. And we have to state that it's at the 5% level of significance. That means we're allowing for an error of